Alright, so now let's go back to my terrible drawing where I was trying to do this. And instead of these lines and everything, I'm just going to draw the interference lines. So that means I'm going to draw I'm going to draw the double slit, that's what it's called, 2 holes, double slit screen. And then I'm going to draw the interference pattern, the straight line here, the constructive interference. I'm going to draw like the fan kind of picture, okay? So, what do we get? We've got our teeny tiny double slit interference, tiny X-Acto knife width, or tiny. And then over here we're going to have a screen or a wall or something like that. So this is our double slit. And then we'll play with maybe blue light, I guess. So my first constructive interference path is that one. Then we could have another one like this. Let's put it right there. And then another one like that. Pretend like they're all starting at the same place. My drawing's not very pretty. And then here. And then here. Okay. So what we see when we have constructive interference of light is we see a bright spot here, and this is called the central bright. It is located directly across the midpoint between the 2 openings, so it's in the center. Then we'll have another bright, and they're called fringes. I think it's like an old dude word. I would have called them spots. I think we probably would have called them spots if we were using language that we use today, but the old dudes use the phrase fringe. So we've got a bright fringe here, or a bright spot, and a bright spot here, and then a bright fringe or bright spot. We've got another bright here and another bright here. And in between your brights, you have dark. D for dark. Dark, that means no light. There's no light on the screen. Now, this first bright above the central bright we call M, and it is a +1. And this one, its M number, its fringe number or spot number is a +2. So what do you think the first one below the central bright will be? -1. -1, -1. And then the second one, -2. So the sign just gives me an idea of which one we're talking about. If you're talking about -3, then I know it's the third one below the central bright. Okay. And what do you think about the M +1, the +1 bright fringe's position compared to the -1 bright fringe's position? What do you think about the difference in the position of this one and that one? They're the same distance, but one is below and one is above. That's perfect. Now, we can also get interference with sound waves. So we can use 2 little tiny slits and let light go through and be split into 2 bits. Or, if you think about this, what if this were 2 little speakers? This could be 2 speakers making the same frequency, hum, and you would get this interference pattern. If you've ever walked around sometime a big stadium or something like that, or a concert or whatever, you might have noticed that there are places where you can hear the music really well and places where you don't hear it very well. And that's because of the interference. Okay. Now we can do some geometry and label some things. Let's call the distance from the slits to the screen L. Let's call the distance between the 2 slits, the 2 tiny openings, D. And then let's call the distance from the central bright to one of the bright fringes, let's call that Y. It could be M1, it could be M2. I'm doing bright +2, so that you'll see that it doesn't have to always be 1. Now, I've got what looks like a triangle. I've got the central bright constructive interference line. I've got Y, the distance from the central bright to my second bright fringe. And then I've got this line that goes back, that constructive interference line. What's this going to be called? Is that a theta? An angle? Okay. Now, how could I relate this angle to the distance I can measure from the screen to the slits and the distance I can measure on the screen for Y? Could I find theta? Any ideas? Yeah, I could use the tan function. So tan theta is equal to Y over L, where Y is the distance from the central bright, so I'm abbreviating, to the mth bright fringe, and L is the distance from the slits to the screen. And theta is the angle between the central constructive interference line and the interference line going to the mth fringe. So that's how I'm going to define that. So between the central constructive interference line and the mth bright fringe constructive interference line. You don't have to write all that out if you can look at that picture and understand that theta is between here and there. But in words, that's what I would call it. The angle between the central constructive interference line and the mth, that's MTH, the mth bright fringe constructive interference line. Okay, now here comes the tricky, fun geometry. Are we ready? Okay, so we've got this interference pattern. Now the only way we can get this interference pattern is if our wave that leaves the bottom opening has a crest at this place, and the wave that leaves the top opening has a crest at that place. We'll find out. Okay, so the light has to leave the bottom. So I've got to have a crest here from the bottom opening, and from the top opening I've got to have a crest reach that point. Okay, now which wave has further to go? The one that leaves the top opening or the one that leaves the bottom opening? The bottom opening has a little bit more distance to go. It has a path difference, right? So if I drop a perpendicular down right here, can y'all see that? Sort of. Okay. This winds up being theta from some other geometry that we're not going to get into right this second, but that is also theta, or very, very close to being theta, similar triangle business. Okay. And then this right here is the extra distance, or the path difference, that the bottom wave has to go through. Now that's a tiny little triangle, so I'm going to blow it up and make it look bigger, just like we were in, biology or something. So we have D, the distance between the two openings. We have the pink, and then this was the path difference right here, and pardon my terrible drawing. And this right here is theta. So how can we find the path difference, this right here, if we have D and theta, and this is a right angle triangle? So if we use the sine of theta, that would be opposite, that would be the path difference, divided by the distance between the two openings. So I want that to be D sine theta is equal to the path difference. And what does the path difference need to be if it's going to be constructive interference? A whole integer of the wavelength. 1, 2, 3, 4, a whole integer. So that right there so that also relates to the wavelength of the light or sound that is passing through or produced by the speakers or something like that. So D is the slit separation. Lambda is still the same angle as before. See above, because that was like a whatever. M is the number of bright fringe. And lambda is the wavelength. Now when it comes to light, you're given wavelength in nanometers. So what do we need to do with nanometers? Any ideas? We have to change it to meters. Does anybody remember what nano stands for? Yes, it's times 10 to the negative 9. That's right. So just be aware of that as you're solving any problems. Okay, so I like this setup because this shows like a yellow laser shown on or incident on a double slit, and it looks like two tiny little lines right there on this index card of science. And then we see on the screen here a central bright for the yellow here. Do you see the two dark spots? And then your +1 and your -1 M's, or whatever you want to call it. So what do you think is going to happen as we decrease the wavelength? So I'm going to take it down to like blue or indigo light. What's going to happen? Any ideas? So I decreased lambda. Hop over here and look. I decreased lambda. What happens to theta? It decreased. So we see a lot more fringes on the screen.